In London Futurist podcast, two subjects we look at a lot are exponential impact and AI. And in both cases, we seek to be visionary, but at the same time realistic. For example, exponential impact often isn't as smooth as you would think by looking at these lovely curves on people's graphs. Instead, there are long periods of disappointments and then what some writers call jolts, or jerks, or big bangs, when things suddenly take on a whole new importance. And one of these happened in AI around 2012. Calum calls that the Big Bang, don't you, Calum?
I do, although I certainly don't claim to have invented that term for it. As you say, progress is not always smooth, and that's for a couple of reasons. One is that technology can march along on its own sweet, merry pace, but it has to be adopted by humans. It has to be fitted in with human institutions. People have to get used to it. And the other is that very often 2 or 3 streams of technology need to come together before something really powerful is available, and they may be marching to different tunes. But yeah, the Big Bang in 2012 was a very important moment in the history of AI.
So how did it come about, and what can we learn from how it came about?
Well, as we'll explore, there was a series of factors, but certainly one of the biggest, if not the biggest, is Moore's Law. There's a lot to say about Moore's Law. Gordon Moore was working for a company called Fairchild Semiconductors in 1965 when he published a paper in which he observed that the number of transistors being placed on a chip was doubling every year. He published this paper and he forecast that it would continue for a decade, and his contemporaries thought he was nuts. He went on to co-found Intel in 1968, and it wasn't until a few years after that that a professor at Caltech called Carver Mead coined the term Moore's Law, and curiously nobody seems to know exactly when that happened. Now, an interesting thing about Moore's Law is that it has changed, it's transformed a lot during its life. In 1965, Gordon Moore thought the doubling period was every year. In 1975, he adjusted that to every 2 years, but a little after that, a colleague of Moore's at Intel called David House noticed that not only were the number of transistors on a chip doubling, but also the performance of each individual transistor was improving, so the period became 18 months, and it stuck at that level for quite a long time. It wasn't just the number of transistors or the quality, it was also their speed. There were regular increases in the clock speeds of computer chips, but that stopped in around about 2004 because of overheating. There was a kind of a cadence to the development of chips, particularly from Intel, which at the time was the Goliath in chip manufacturing. Since 2007, Intel had this tick-tock cadence. The tick was improvements in the manufacturing process, which enabled chip sizes to be reduced. And chip sizes was a very important part of the business of getting more transistors on. And the tock was improvements in the architecture. And that carried on till about 2015, when the cadence slowed down. It slowed down to about 2.5 years, and the cadence changed. One observer said it moved from tick-tock to tic-tac-toe, which represented process improvements, that was the tick, architecture, that was the tack, and optimization and efficiency, that's the toe.
So what's coming after tic-tac-toe?
There's a lot more to come. A development which has been very, very important was the arrival of GPUs. Most of the chips that I've been talking about so far were CPUs, that's Central Process Unit, and a type of chip called a GPU, which stands for Graphical Process Unit, was developed for video games for rendering visual scenes. And it turned out that GPUs were extremely good for machine learning, and we'll come to what machine learning is in a while. So GPUs came along and greatly improved the industry. And then another development was tensor processing units, or TPUs. So you've got CPUs, GPUs, and TPUs. Tensor processing units operate at very high speeds, but with lower precision, and they are particularly good for machine learning applications. A lot of people say that Moore's Law is dead or dying. This is very controversial. As far as I can see, it's not. It's just continuing to evolve. There are a lot of ways of keeping it going. I've already talked about GPUs and TPUs. These are different chip architectures. There will no doubt be other revolutions along those lines coming that we don't even know about. But some things that we can see, there will be three-dimensional chips. At the moment, chips are essentially 2D laid out on flat planes. And it's hard to create 3D chips because the layers need to be connected up and attaching wires between them is very tricky. And also, there's always the danger that each layer will overheat the layer above and below. So it's a hard technology to get right, but there's lots of people working on it. Another route for improvement is to store the data that a processor is using on the same chip as the processing unit. Currently, almost all chips have data in one place and the processing in another. To combine them, you have a chip called a Memristor, and that's another important development. There is also neuromorphic computing.
So that's when more of the architecture of the human brain might be mimicked in some way in these chips. After all, the human brain seems to be more power efficient than some of these chips by an order of magnitude. So whatever's going on inside the human brain, if we understand that and teams at Intel are looking at it, then there's a chance that we will have more breakthroughs in our silicon chips.
That's exactly right. A human brain uses about the energy of a light bulb, and to do the same amount of processing as a human brain does when it's recognizing faces, you need the energy of a village or a small town. Neuromorphic computing attempts to address that by, as you say, making chips operate in a way more akin to neurons. They spike, they are more analog than digital, and that's a whole subject that I think we should probably do a whole podcast on. It's certainly a big subject. And then, of course, the big daddy of all, the future opportunities to continue speeding up the performance of computers, is something that you know a lot more than I do about, David, which is quantum computing.
Quantum computing is still at a very early stage, and frankly, we can only guess in broad terms what is going to be enabled by breakthroughs in quantum computing. What makes it even more interesting is that there are multiple types of quantum computing. It's almost like in the early days of semiconductors, people disputed whether it would be silicon or germanium, a different semiconductor. And we don't have Germanium Valley, we have Silicon Valley. In terms of what quantum computers are going to be truly successful, there's about 4 or 5 different options. Let's discuss them in a future episode. Quantum computers can't do everything that classical computers can do, but there are some things they can do remarkably faster. And once we know about that, we can change our algorithms to take advantage of that, a bit like the way deep learning algorithms are now tailored to the special processing characteristics of first GPUs and then TPUs. So progress comes not just when one trend goes off on its own, but it's when several different trends can be made to interact, to converge constructively.
That's right. And yes, I definitely think we need a whole episode on quantum computing, and I'm going to learn a lot during that one. Now, Moore's law is a fascinating phenomenon, and it's very powerful. Exponential growth, to be specific, exponential growth to the power of 2, or to the factor of 2, is incredibly powerful. When you double something routinely, you get remarkable effects. If, and it is an if, Moore's law continues for, say, 30 years, the power of the computers, the performance ability of the computers that we have in 10 years' time would be 120 times greater than what we have today. And that's a lot. But if you project a bit further, things get really remarkable. In 20 years' time, they would be 8,000 times as powerful as the computers we have today. And in 30 years, they would be 1 million times more powerful than the computers today. It's very hard to imagine what those machines will be able to do. Now, if you look backwards, we have had that kind of growth. And that's why the smartphone in our pocket is more powerful than the Cray supercomputer was in the 70s. A few years ago, somebody estimated that if you could have built an iPhone in the 1960s, you couldn't have, but if you could, it would have occupied a building. I think it was 300 stories high and 30 blocks wide, and would have consumed half the electricity of the world that the world was using at the time. And because of Moore's law, because our machines have got so much more powerful, that amount of power now sits in all of our pockets. Now, of course, exponential growth never continues forever. If it did, it would take over the universe. But we see exponential growth in some areas of everyday life. And for instance, our cells. An adult human is composed of about 27 trillion cells, and they were created by fission. the division in half, which is an exponential process. And it takes about 46 steps of fission to create all of the cells in an adult human. Moore's law, by comparison, has had about 39 steps in the 55 to 60 years of its existence. So there's no a priori reason why Moore's law is coming to an end now, and there's lots of ways to keep it going. That doesn't mean it definitely will keep going. It doesn't mean it definitely will keep going for 30 years, but it looks like there's a pretty reasonable chance.
Well, let's look at some reasons people offer as to why Moore's law will come to an end. And I think there are three that people point to. They suggest that there's no more scope in the physics, that once you've got down to semiconductors that are just one atom wide or so, then you can't do anything more. So that's one limit. Another limit is the amount of processing fabrication that's required. So Intel's labs got bigger and bigger to make these more powerful chips. The argument is that it's just too economically infeasible. Or thirdly, that even if it was economically feasible at a stretch, then society would decide this just isn't worth our interests. So the counter-arguments are that there is more physics ahead. As you pointed out, there's not just two-dimensional chips, there are three-dimensional chips, and there's all kinds of quantum possibilities, and there's all kinds of possibilities from neuromorphic computing. In terms of the scale of the fabrication plants, well, there's innovation there too. It's not just Intel, it's also new companies, comparatively new companies like NVIDIA and many others who are entering. Some startups even have got the ambition to develop new kinds of chips specially suited for the tasks of machine learning. And in terms of whether humanity wants to go there or not, with the costs involved, I think there are plenty of reasons we can explore why humanity would be grateful for even more powerful chips.
I think that's absolutely right. And another point about the scale issue, it is true that chips are getting unfeasibly small, but as Richard Feynman, the famous physicist, said, there's plenty more room at the bottom. You can manipulate information by operating at subatomic levels if you have the technology. And doubtless, initially, each new technology will be very, very expensive. The issue is, does it create benefits that outweigh those costs? And if it does, then it will be introduced. And if one jurisdiction says, no, that's too much effort, or it's not the right use of resources, and decides not to deploy a new technology, it'll find itself becoming uneconomic, unenviable by comparison with places that do deploy it. So it's very hard for us to decide not to do something which is economically or in other ways valuable.
I would also make the point from my own background in the mobile computing and smartphone industry that often with clever software or with clever algorithms, you can learn to do things more efficiently than before. So there's a certain kind of progress that comes just by scaling things up with more than before, but there's also a very important set of progresses possible by finding better functions, better algorithms. And if we look at what made the Big Bang possible, in part it was the use of GPUs, the very clever use of GPUs to do the matrix multiplication that's at the heart of many of the calculations of deep learning. But in part it was some simplifications, things that allowed the mathematics to run more smoothly, and so that less processing power would be needed.
It used to be said, I think it was Bill Gates said, that hardware giveth and software taketh away. In other words, you get a more powerful machine, but the latest version of Microsoft bloatware operating system requires all that extra hardware grunt in order to do something not much better than what it did before. But as a senior executive at Microsoft, Chris Bishop, said, there's actually a new Moore's law in software. Software is allowing machines to get even more powerful alongside the improvements in hardware.
And there is some work by teams in Google to use AI to lay out chips more intelligently, to find ways of arranging the components so that for the same input of electrical energy, they are more effective in what they can compute. So there's a very useful positive feedback cycle there. Better AI allows the design of better chips, which allows better AI.
Exactly. And as well as having better hardware, better software, in order to operate today's cutting-edge AI systems, you need lots and lots of data, labeled data. And so some of the databases that have been developed were critical to the Big Bang. And David, I think you have a particular insight into ImageNet.
ImageNet came about because a professor called Fei Li at Stanford wanted to generate lots of data of images which were labeled and could then be used for training. And she took advantage of another kind of AI system called Amazon Turk, which is a way in which humans could respond to requests to supply some information and be paid a small amount for it. So she fed lots of images into Amazon Turk, and she had different humans say what they thought was in the images. And by weighing up what people thought and looking at more than one answer each time, she ended up with this vast data set called ImageNet, which in turn was then used not only to train visual processing AIs, but also to evaluate the progress of visual processing AIs. The search for labeled data is ongoing. One of the reasons why AIs can misperform is if there are mistakes in the labeling or biases in the labeling. And one of the ways in which AIs therefore get better is when one AI can generate realistic looking images and label it accurately. It could label it very accurately because it knows exactly what is put in the image. And then this can be sent to other AIs to train them. So now we're able to dispense often with the human in the loop, which, despite being wonderfully generally intelligent, we humans do occasionally make mistakes. And that's another reason why things can speed up even more.
So all of this came together, Moore's law, better algorithms, better data, to create the Big Bang of 2012. And specifically, what happened in 2012 was some researchers, led by Geoff Hinton, got an algorithm called backpropagation to work, which is a kind of machine learning, and we'll explain later what machine learning is. There are people who get a bit annoyed about Hinton being credited for this. There were a lot of people working on machine learning for decades before. Machine learning was launched really in about 1959 by Arthur Samuel. And Jürgen Schmidhuber is one particular researcher who does get cross that he and other colleagues aren't given similar sort of credit for being pioneers. He developed something called long short-term memory back in 1997, and he feels that's underplayed. But nevertheless, for whatever reason, Geoff Hinton and a couple of other researchers, Jan LeCun, who's now at Facebook, and Joshua Bengio, who works closely with Microsoft, are the three who are typically associated with the Big Bang in 2012. And what happened as a result of the Big Bang, which really makes the whole thing significant, is that AI started to make money. AI had done significant things before the Big Bang. It had beaten the world's best chess player. It had beaten the world's best player of TV quiz called Jeopardy. But it didn't really make money. And shortly after the 2012 Big Bang, it started to make money. And as we've said before, specifically, Google and Facebook started to take a lot of the advertising industry away from the mainstream media. And we had in 2015, by the time this was really getting going and people started to realise, journalists particularly started to realise what was happening, we had the great robot freakout of 2015. We had Droid Dread, in which pretty much every newspaper had a picture of the Terminator every day saying, uh-oh, machines are coming to take our jobs, they're coming to take over everything from us. So that's when people became aware of it. But the fundamental thing that happened was that after the Big Bang, AI started to make money.
Not just in one field. What was really interesting is that the particular innovations applied to one type of neural network called a convolutional neural network, which was able to process images, but very similar breakthroughs could be applied in understanding text. This is called a recurrent neural network, which understands the context of the few words that were said before to figure out what the next word is most likely to be. And this, by the way, is where Jürgen Schmidhuber's earlier work on long short-term memory made some difference. It was applied in these recurrent neural networks, so there were improvements in speech recognition, and more or less the same set of ideas could be applied in speech translation. I understand that at about this time, or a few years later, people said that by switching to this new architecture from their previous machine learning architecture, they had made more progress in just a few months than in many years prior to that. So the Big Bang was successful not just in a breakthrough in one area, but in multiple areas.
That's right. I think we probably have to get into a description of machine learning and deep learning. And this is quite tricky, but it's something we've got to grapple with. As I said, machine learning is a term coined by Arthur Samuel around 1959. It means computer algorithms that improve automatically through experience. They take decisions or deliver results which they weren't specifically programmed to do. They ingest a great deal of data, training data, they build mathematical models, and they produce the results without being explicitly programmed. It's been described as like successfully boiling the ocean. So something that strategy consultants are told to do is never just go and collect a whole load of data about a particular business problem that you're trying to tackle. First of all, have a hypothesis. Take a scientific approach to the problem. Develop a hypothesis about what the problem is likely to be caused by. Then go and look for data which will either confirm or refute that hypothesis. Boiling the ocean is the opposite of that, where you simply go and collect all the data and see what comes out. Machine learning is boiling the ocean. It's assembling as much data as you possibly can about a subject and allowing a machine to sift through that data and find patterns which a human wouldn't be able to do, because a human can't simultaneously look at millions and millions of data points. A machine can do that. So that's one way of thinking about what machine learning is. A subset of machine learning is deep learning, and the characteristic of deep learning is that processing happens in levels. So at the bottom level, the machine will review data and identify some characteristics. It'll pass those identifications up to the next layer, which is pre-armed to look for particular patterns. When it receives an alert that that particular pattern has cropped up, it wakes up and checks it and then passes it to the next level above. So in a deep learning system, which are typically 10 layers or sometimes many more than that, the data is processed in a series of layers.
One example might be that at one layer it's just looking at the colors of different parts of the screen. Another level up is noticing lines and curves. Another level further up is noticing things that might look like eyes, things like might look like noses, things like might look like mouths. And another level up is saying, hey, in that case, this looks like a face. And another level up might say, hey, this looks like a picture of Marilyn Monroe or Albert Einstein. And although we think we understand roughly what the various levels might do, when there's deep levels involved, it's often a bit of a black box, and we're not quite sure which concepts the different levels are focusing on. But we do know that after they've been trained, they can make a remarkably good job at distinguishing different images, or, as I said, understanding what text is, or turning it from one language into another.
We'll be right back after a quick break.
The People in Performance podcast offers insights into the strategic competencies, behaviors, and results needed to increase the performance of employees and leaders. The show looks at all areas of the world of work, including attraction and recruitment, onboarding, training, and succession planning. Tune in to get a better handle on the stages of workforce planning you need to master in order to guarantee long-term success in a rapidly changing world of work. New episodes drop each week. Check out the latest People in Performance episodes on your podcast platform of choice. Follow us on socials and read the latest articles at pppod.com.
And so machines now are better at facial recognition than humans are, which is really quite remarkable. It wasn't expected 15 or 20 years ago that would happen. Machine learning can be supervised, unsupervised, or involve reinforcement learning. And this is where the data comes in. So in supervised learning, the machine is given pre-labeled data. So in the case of faces, the data might say this is a human face. In fact, this is Marilyn Monroe's face. In fact, this is Marilyn Monroe's face looking towards the light. In unsupervised learning, the machine isn't given any pointers and has to identify the inputs and the outputs as well as the rules that connect them. And not surprisingly, that's rather hard. And there's a third version, which is reinforcement learning, and this is where DeepMind has made a lot of progress. In reinforcement learning, the system gets feedback from the environment. For instance, playing a video game, it's given the score. It might only be given the score. It might not get told what the aim of the game is, it might not be told what the rules of the game are, but it's just given the score and told, maximize that score. And then there's variants of these three types: supervised, unsupervised, and reinforcement. There is deep reinforcement learning, and actually that's DeepMind's speciality. And there's also self-supervised learning. Self-supervised learning is where the machine finds and uses labels which are already in the data, although they may not be explicitly related to different aspects of the data. We need also to explain a bit more about deep learning. The very nice illustration or example of deep learning is Yann LeCun, who I mentioned before was a peer of Jeff Hinton, one of the three people who gets credited with the Big Bang in 2012 and works for Facebook. He described it as like a black box with a camera at one end and a green light and a red light on the top and a whole bunch of knobs on the front. And the algorithm tries to adjust the knobs so that when a target image, say for instance a dog, is in front of the camera, the red light turns on, and when an alternate target image, say a car, is in front of the camera, the green light turns on. So you've got the camera looking at an image, you've got red and green light on the top and a bunch of knobs in the front, and the algorithm is trying to get the light to go red if it's a dog and green if it's a car. So if you show the camera a dog and the red is already bright, you don't do anything. If it's dim, if there is a red light on but it's dim, you just tweak the knobs so that the light gets brighter. Same with the car. If the green light's on, that's fine when the camera's seeing a car. But if it's dim or if you've got a red light on, you tweak the knobs until the green light goes on properly. And if you show the box enough examples of cars and dogs and you keep adjusting the knobs a little bit each time, eventually the machine will get the right answer every time. Now, a large-scale deep learning system, he said, imagine a box that's got 500 million knobs, 1,000 light bulbs, and 10 million images to train it. That's a deep learning system. I find that description very helpful.
These black box methods are remarkable, but I want to put on record for future discussions that I also consider them to be dangerous. They may work in many circumstances, but it's not clear why they work. The knobs have been twiddled and twiddled and twiddled, and in reality takes place by the complex matrix multiplications that we mentioned earlier. They've been twiddled so much that the results fit the training data, and generally they'll also work on similar data to the data that was in the training set. But from time to time, the same system will get a new case completely wrong. It turns out that what's been learned isn't quite as obvious as what we thought it was. It might have noticed, for example, that in one set of circumstances there was always something in the background, pictures of wolves versus pictures of dogs. If there are humans in the background, it's probably a dog rather than a wolf. That's a fairly simple example, but in many more complex ways, an AI can get the right answer 99.9% of the time until it gets it wrong on the 1000th occasion. So long as everybody's checking and testing, that's no big deal. But if we have set these AIs in control of parts of our society, that could be very bad indeed. At the very least, it can cause people to be upset when they are misclassified, as sadly some people's faces were misclassified as, "Hey, looks like a gorilla," when in fact they were different from any of the mainly white faces that had been in the training set. So for that reason, I have only two cheers for black box learning. We need to move as quickly as possible to systems that can explain themselves and authentically explain themselves. And that's a subject we'll come back to. Not AI, but XAI, explainable AI.
Yes, if that is really achievable, given that the reason why these machines do so well is that they are wading through vast oceans of data and finding patterns that humans can't. I'm not even sure that if they said to us, the reason why I've identified this as being the answer to your question is that row 393,000 and column 2,023 aligns with the data in this other cross-section of rows and columns elsewhere, and gives you a list of 100 points like that, well, it means nothing to a human mind. So I'm slightly sceptical about explainable AI. I think we may have to accept, and I'd be delighted to be proved wrong or told I'm wrong, I think we may have to accept that some AI, some of the most powerful AI, simply can't be understood by humans. It's not, for all practical purposes, explainable. But I think we'll need to come back to that, and there's a whole lot of other issues about AI, because as you're right, and it's a brittle set of systems, there are serious downsides to its misuse or its inadvertent misuse, as well as this explainability, there's transparency, there's privacy, there's something called algocracy. I think we will need to come back to that. In fact, I think we'll need to come back to the short-term future of AI in probably the next episode.
I'd just like to put one trailer out for one thing we'll talk about fairly soon in another episode, and that is the possibility that there's already another Big Bang underway. You pointed out, Calum, that the events in 2012 were only understood by a small group of people for a few years, and then 3 years later there was much more social reaction. It's possible that around 2019 another kind of Big Bang has taken place, which involves what people call large language models, and people have probably heard of GPT-2 and GPT-3. They're not just significant in that they have scanned much larger sets of text than ever before. Enormous numbers of books, enormous numbers of Wikipedia pages, Reddit posts, and so on. But they have had changes in their algorithms, and they can now do something called few-shot learning or transfer learning, which means they can be trained very well in a whole set of general data, and then they can be shown a pattern. And in this pattern, a few examples are shown, and the system is then able to generate more along the same lines. So instead of needing each new time to be shown a million pictures of something new before it realizes what it is, it's able to instantiate more quickly. This has resulted in AIs that can produce remarkably interesting pictures that no longer suffer from the uncanny valley effect when we say, well, that's quite human but not human enough and it makes me feel uncomfortable. Things like DALL-E or DALL-E 2. It's also resulted in chatbots, which have persuaded some observers, not me yet, that they are conscious. And there is the most recent thing called Gato, in which a system was trained to be able to do, I think, 604 different types of things at once, and could quickly learn a new task as well. So this, I think, could be the start of something that might be even more significant than the deep learning Big Bang. It doesn't have a proper name yet, but that's something we can explore, possibly with the help of a guest.
I look forward to that.
So look out for more episodes of London Futurists podcast. This is me, David Booth, signing off.
And me, Calum Chace, signing off.